Hi everyone, welcome to our second video on functions of several variables. The goal of this video is to take a further look at surfaces. So recall that the graph of an equation of more than one variable is called a surface, and you see a couple of nice ones here on the screen. And the goal of this video is to help you start to be able to visualize and sketch a surface given the equation. So just like we know from our old math classes, if we see y equals x squared, we know that we're drawing a parabola. And so the idea is to be able to get that comfortable with some of these equations that have more than one variable. So we're going to start with just a catalog of kind of the most important surfaces, and then we'll get a little more creative. All right, so we're going to start with the most basic surface of all, and these are our planes. Recall from chapter 12 that the basic equation of a plane is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And this represents a plane, recall, that has normal vector ABC and that contains the point x naught, y naught, z naught. Now, we rearrange this equation and we can write it like ax plus by plus cz equals d. And that's normally what we'll see our equations of our planes looking like. So for example, something like z equals 8 minus 2x minus 4y, which is the equation of the plane that we see here on the screen. We could also have equations that look like z equals 3, that would be a horizontal plane, or y equals 4, which would be a vertical plane. And we'll look at these more in detail shortly. Okay, so those are our planes. Another familiar surface to us from chapter 12 are our spheres. So recall the basic equation of a sphere is something like x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. And this represents a sphere centered at the point x naught, y naught, z naught with radius r. So for example, the sphere that you see pictured here in red has equation x squared plus y squared plus z squared equals 9. So this is a sphere centered at the origin of radius 3. Okay, moving on to some new surfaces. We'll start with cylinders. So the basic equation of a cylinder is something like x squared plus y squared equals r squared, which is going to represent a cylinder centered around the origin of radius r. So for example, the green cylinder on the screen has equation x squared plus y squared equals 4. And so what we have to get used to is with these equations, we're used to seeing an equation like this, an x squared plus y squared equals r squared. But in the xy plane in R2, this equation, of course, represents a circle. And so what we've got to remember is now if we're in R3, there's a z that has to be accounted for. And so in an equation like this, because the z is not included, there's no restrictions on z, that means z can be anything. So that's what turns our circle in the xy plane into a cylinder. It's the fact that z has no restriction and z can be absolutely anything. Here's some more pictures of cylinders. So the first, the x squared plus y squared equals 1. So you can see our unit circle there sitting in the xy plane. And then because z can be anything, that circle becomes a cylinder in R3. Now in figure 3, we have y squared plus z squared equals 1. So that is going to represent a circle in the yz plane, centered at the origin of radius 1. And because there are no restrictions on the variable x, then that's how we know that this is going to be a cylinder that extends around the x-axis. Another example of this idea would be the surface z equals x squared. So in the xz plane, we'll have a nice parabola that's familiar to us. But because now there are no restrictions on the variable y can be anything. So this parabola is going to extend in both directions indefinitely because of that no restriction on the variable y. Okay, so we've talked about planes, we've talked about spheres, and we've talked about cylinders. Up next is our elliptic paraboloids. These are like our three-dimensional parabolas. So the basic equation for an elliptic paraboloid looks something like this. Z equals C times x squared over a squared plus y squared over b squared. So a basic example of an elliptic paraboloid might be just z equals x squared plus y squared. And so how are we going to remember this shape from the equation? Well, I kind of think of the variables one at a time. So if you think just about what's happening in the xz plane, if you ignore the y variable altogether, and I'm also going to ignore the constants, the c and the a squared, because those constants don't change the basic shape. Okay, so if we ignore everything else and just focus on the z and the x, we have a z equals x squared. So that tells us that in our xz plane, we're going to expect to see a parabola that's opening upward. Similarly, in the yz plane, if we ignore everything else except for the z and the y, we have z equals y squared. So in the yz plane, we're also going to expect to see a parabola opening upward. And so when we put those two pieces together, we get this three-dimensional parabola, this elliptic paraboloid. And let's compare that with what happens in the next example, our hyperbolic paraboloid. So the basic equation for a hyperbolic paraboloid is z equals c times x squared over a squared minus y squared over b squared. So a basic example might be z equals 1/10 x squared minus y squared. All right, so let's use that same logic that we had in the last example. If we think about what's happening in the xz plane, so if we only focus on the x and z variables, we have z equals x squared, again, a parabola opening upward. But compare that to what's happening in the yz plane. So this time, focusing only on the z and the y, we have z equals minus y squared. And that, of course, is a parabola that's been turned upside down. And so because in the one plane we have a parabola opening upward, and in the other plane we have a parabola opening downward, that's what causes this equation to look like this hyperbolic paraboloid instead. Great. One more basic equation for us, and it's the equation of a cone. So our basic equation here would be z squared over c squared equals x squared over a squared plus y squared over b squared. So for example, something like z squared equals x squared plus y squared. And to help us remember, let's go through that logic one more time. If we think about what's happening in the xz plane, so if we only focus on the variables x and z, this time we would have z squared equals x squared. Or if we take a square root, right, we'd have z equals positive and negative x. And so that's why we get these straight lines, this straight line z equals x and a straight line z equals negative x. And the same thing is true in the yz plane. We would have z squared equals y squared, or we can think of that as z equals plus or minus y. So that's going to give us those straight lines, and that's what's going to cause this cone shape. Now, one last remark about our cone is, what if you have an equation that looks like the positive square root? That would represent just the top half of the cone. Similarly, if you had the negative square root, that would of course represent only the bottom half of the cone. All right, and now we're going to do something a little bit different. I'm going to head over to Geogebra to help us explore these surfaces a little bit more. So let's go. Okay, so here we are now at Geogebra, which is a free website that's really nice for helping us visualize some of these surfaces. And so I want to run through some of the ones we've talked about already, starting with our planes. So recall we started with the plane z equals 8 minus 2x minus 4y. And I'm going to move the picture around a little bit here. All right, so here now now we can see the intersection of this plane along the x-axis. Our intersection point is at the point 4, 0, 0. And we intersect along the y-axis at the point 0, 2, 0. And it's not on our chart, but our intersection point along the z-axis would be 0, 0, 8. So there's the plane that we started with. And let's compare that to our horizontal plane. There's our horizontal plane, z equals 3. And our vertical plane, y equals 4. So let me rotate us around a little bit so you can see that horizontal plane happening at y equals 4. Nice. So here are just 3 examples of planes to get us started. All right, great. Up next, we have our sphere, right? So again, there's our sphere, x squared plus y squared plus z squared equals 9. So a sphere centered at the origin of radius 3. And we'll compare that to our cylinder, x squared plus y squared equals 4. So our cylinder centered at the origin of radius 2. And there's x squared plus z squared equals 4. All right, so in the x squared plus z squared equals 4, notice that in the xz plane, I'm going to move us around to the xz plane. There we are. So in the xz plane, you can see just that circle centered at the origin of radius 2. But then because there are no restrictions on y, we see that this sphere is going to extend itself along the y-axis. Great. Okay, up next, let's move on to our paraboloids. Okay, so here is our nice elliptic paraboloid, z equals x squared plus y squared. And I'm going to be moving us around a little bit between the xz plane and the yz plane. So to help us keep those straight, I'm going to plot a point A along the x-axis and a point B along the y-axis. Okay. All right, so now we can see in the xz plane that sure enough we have what looks like a parabola opening upward. And similarly, in the YZ plane, we also just have a parabola opening upward. Okay, we're going to compare that to our hyperbolic paraboloid. So here I have 1/10 times x squared minus y squared. And so now we see, because of the z equals minus y squared, that in the YZ plane, we have what looks like a parabola opening downward. And we're going to compare that to what's happening in the XZ plane. There we go. So in the XZ plane, because it's a z equals x squared, we have a parabola opening upward. And so that's just meant to help us compare those two, the elliptic versus the hyperbolic paraboloids. Great. Our last basic shape was our cone, and so there's a nice picture of a cone. So a z squared equals x squared plus y squared. All right, great. Okay, so what we're going to do now is just sketch some surfaces. So starting with the following, we're going to sketch the region bounded by the surfaces z equals 3x squared plus 3y squared, and z equals 4 minus x squared minus y squared. Okay, now the 3x squared plus 3y squared, thinking about what's happening just in the xz plane, we have a parabola opening upward. And in the YZ plane, we have a parabola opening upward. So that's an elliptic paraboloid, right? And we're going to hop over to Geogebra to see that picture. So there's our 3x squared plus 3y squared. And then the other surface we had in our example was 4 minus x squared minus y squared. And that makes sense because if you think about what's happening in the xz plane, that is going to look like a parabola that has been flipped upside down and moved up 4 units on the axis. So here's our parabola that's been flipped upside down and moved up 4 units on the axis, similarly in the YZ plane. And so if we want the intersection of these two surfaces, it's going to look like this region that we see here. That's the intersection of those two surfaces. Great. All right, so our second example is to sketch the region bounded within the surface x squared plus y squared equals 1, below z equals 4, and above z equals 1 minus x squared minus y squared. So let's kind of get the mental picture and then we'll hop over to Geogebra to see it. So x squared plus y squared equals 1 is going to be a cylinder, right? It's going to be a cylinder that looks like the unit circle in the xy plane, but then extends symmetric around z forever. But we're going to cap it off in the top by a horizontal plane, z equals 4. And then we're going to cap it off in the bottom by a paraboloid. The 1 minus x squared tells us we've got a parabola flipped upside down and moved up 1 unit. And the same thing is true for the 1 minus y squared. All right, so let's see. So we start with a cylinder that we're going to cut off in the top by a horizontal plane, z equals 4. And we're going to cut in the bottom by an elliptic paraboloid that's been flipped upside down and moved up 1 unit. And so the region we're interested in is the region inside this cylinder, below this horizontal plane, and above this elliptic paraboloid. We're going to do one more like that. Okay, so our last example like this. Let's sketch the region bounded by the surfaces. Z equals the square root of x squared plus y squared, and z equals 2. Okay, so z equals 2, that's easy enough. That's a horizontal plane. All right, now the z equals the square root of x squared plus y squared. So focusing on just the xz, that would look like z equals x. So that straight line. And similarly, focusing on the yz's, we basically have z equals y. So this is the top half of a cone. So we want the top half of a cone, but we want it bounded on top by a horizontal plane, z equals 2. Let's go over to Geogebra and take a look. Okay, so here is our cone. And we're going to bound that cone by the plane z equals 2. So the region that we're interested in is this region that we see here, this inside of this cone, but lying below the horizontal plane, z equals 2. Great, so thanks for your patience with going back and forth. Here's a recap. So there was the region we found bounded between those two elliptic paraboloids. Here was the region we found inside the cylinder between a horizontal plane and an elliptic paraboloid. And here's another picture kind of zooming in on the region we're interested in. And here was the region we found that was between the cone and the plane. And then here's another picture also of that region just to give you another visualization. Great. All right, so that's all for this video. There's one final video on section 14.1 on level curves, and I'll see you then. Thanks, guys. Bye.